Namaskar. I'm Shivani Jha and I welcome you all to our live and interactive session. You are watching this session on PM eVidya channel number 10 and also on our official YouTube handle, that is NCERT official. Well, let me apprise you all, for this half an hour we have our special session for class 10th students, and the subject for today is of course science, and the topic that we have taken up today is magnetic effects of electric current. Well, what is magnetic effects and what are we going to learn in this session? So, to delve deeper into this entire topic, we are also joined by our expert through online medium. So, please let me introduce to him first. Firstly, we are joined by Mr. Bergin G. Sir is PGT Physics in Government Boys Higher Secondary School in Sayalgudi, Tamilnadu. So, namaskar and welcome to our session.
Good evening, ma'am.
Good evening, sir. So, along with sir, we are also joined by our Indian Sign Language interpreter, who is Mr. Sahib Singh. So, I also welcome you to this session. And now, dear learners, dear students and our viewers, in case if you have any queries or doubt you want to share with us, you can directly contact us via phone or our email ID. Our phone number is flashing on your screens, which is 8800440559, and our email ID is dth.class10@ciet.nic.in. And yes, as you all know, this session of ours is live and interactive. So, you can also drop your comments, your queries or any of your questions in the live chat box option. So, now let us begin our today's topic, which is magnetic effects of electric current. So, firstly, Mr. Bergin sir, I would like to ask you, what are we going to cover in today's topic, that is magnetic effects. So, can we have brief about that?
Okay, good evening to every viewers. In today's session, we are going to discuss on the topic magnetic effect of electric current. When electric current is passed through a wire or circuit, heat is generated through the circuit. That is called a heating effect of current. Similarly, when electric current is passed through some solution, some electrolysis happening. That is chemical effect of current. Like that, when electric current is passed through a wire or conducting material, magnetic field is created around that conductor. That type of effect is called the magnetic effect of electric current. In today's session, we are going to discuss some of the questions that are asked in magnetic effect of electric current.
Okay, sir. So, the first question which I want to ask you, can you explain the expected behavior of the compass needle when it is placed near a bar magnet, if we talk about magnetic effects here?
Yes. Bar magnet is a natural magnet. Naturally, it has
So, we are going to talk about the bar magnet first,
yes,
right,
yes.
sir?
We are going to talk about
which is a natural magnet also, we can say.
Yes, yes. One of the things that we have to know is
Okay, so can we have some points on bar magnet also, sir?
Yes, yes. I will explain. My PPT is stopped, so I just...
Okay, no issue, sir. So, dear all learners, today we are going to talk on magnetic effects of electric current, and for the same, firstly, sir is going to talk on the bar magnetic, and which is also known as natural magnet, on which we are going to talk about. So, please be with us for the whole session. So, Mr. Bergin sir,
yes,
are you available now?
Yes, yes, I am available now.
So
if you take bar magnet is a natural magnet.
Okay.
Natural magnet means it has the property of magnet naturally. If you take that, some forces are around that magnet. When you bring a iron or another magnet, it feels some attraction or repulsion. That area is called a magnetic field. So, the main thing we have to know about this magnet is, we have to know the magnetic field around this magnet. The way how we can find out the magnetic field is, if you keep a north pole near any one of the ends, the behavior of the north pole will give the direction of the magnetic field. For example, if I keep to North Pole near north end, it will repel in this way. So the direction of the magnetic field is at this end is in this direction. In the South Pole, if you look at if you keep the same North Pole in that point, it will attracts towards the south. So if you place any North Pole at any point, the behavior will shows the direction of the magnetic field. In reality, we cannot able to get this North Pole, because if you split this magnet into very, very small tiny particle also, it has both pole, North Pole and South Pole. Then how will you find out the magnetic direction? The path along which a unit North Pole move is the direction of the magnetic field, but in reality, we are using one device called compass box. Compass box is a small magnet with a North Pole and South Pole. If you keep a compass box near to the North Pole, it attracts the South Pole of that needle and it repels the North Pole. So if you repeatedly place the compass box in different places, you will get a pattern like this. So if you analyze the pattern, it look like this. So this is the magnetic field of the bar magnet. Look at this magnetic field. It starts from North Pole and ends to the South Pole outside the magnet. But if you look inside the magnet, it goes from south to north. And also you can observe that inside the magnet, the magnetic field are almost uniform. Outside the magnet, it is not uniform. Now look at here, this is a magnet and some magnetic field lines are described here. Here there are 2 points A and B. Look at this point A and B. If I take a area and place it at the point A, it covers 4 lines. That means 4 lines are passing through that area. If the same area I keep it here near B, only 1 line is passing through the area. So what you understand is, near A, the lines are very close to each other, so the magnetic field is large. At the point B, the lines are very separated. That means they are the distance between the lines are very separated than at the point A. So these lines intensity only gives the magnitude of the magnetic field.
Okay, sir. So here I have another question for you. Sir, can we also compare the magnetic field lines produced by a straight current carrying conductor with those produced by a bar magnet that we have studied thoroughly?
Yes. The bar magnetic field that we studied just now.
Yes.
If you take a straight conductor and when a current I is passed through this straight conductor, a magnetic field is produced around this conductor. That everyone know. But what about the direction of the magnetic field? If you keep your palm like this, we can call this rule as a right hand thumb rule. And if we keep the thumb of our right hand along the direction of the current, then the finger will shows the direction of the magnetic field. Here the finger is showing in this direction. Look at towards left it is showing. So at this point the magnetic field is towards left. So look at this, when I fold the finger, the direction will also changed. So now it is outward to the plane of paper. Then again when I rotate it, the direction of the magnetic field changes. Again it changes. Altogether, if you compare all the direction, you can find that the direction is along a concentric circle. Look at this. So near the wire, the magnetic field is represented by a concentric circle. Now here some dots and Hindu marks are presented here. Now dots means it is going outward. outward to the plane of paper. That means if you consider the screen as a paper and it is coming outward. And the into mark shows that the magnetic lines are going inwards. So if you take any point in a concentric circle, one end is going inward and other end is going outwards. By using this right hand thumb rule, we can easily find out the direction of the magnetic field. Now I am keeping one current carrying conductor in this direction. The current is flowing from left to right. How can we find out the magnetic field? Now I am taking a point P here. I am going to find out the magnetic field at the point P. For that, I keep my thumb along the direction of the current, and the direction of the finger will shows the direction of the magnetic field at the point P. So at the point P, it is going inwards. Do you think that? So I can mark as into mark here. So when you read any book, the magnetic field which is going inward to the plane of paper is represented by this into mark, and a dot it is represented as the magnetic field lines coming out of the plane of paper. Now I am giving another example that current is flowing in this direction towards download in an angle. I am considering 2 points here, P1 and P2. So can you guess what is the magnetic field direction in P1 and P2? In the same way, we can keep the thumb along the direction of the current. At the side P1, it is coming out of the paper. The fingers are coming out of the paper. So we can say that at point P1, the magnetic field is outwards. And at the point P2, if you rotate your fingers, you will get the point. At the point P2, the fingers are going inwards. So we can easily find out the direction at the point P2. That means the magnetic field is inward. So in examination or some other places, if somebody asks what is the direction of the magnetic field in any curve or any shape, if a straight carrying conductor carrying current, then the direction can be find out using this method. So this is the comparison between bar magnet and a straight conductor. For bar magnet, the magnetic field starts at north pole and ends at south pole, but in straight conductor, the magnetic field is in a concentric circle, and the direction of the magnetic field is we can find out using thumb rule.
Okay, sir. So here we got how to find the direction of magnetic field through the help of right hand thumb rule. So here, sir, I would also like to ask another question, like if we talk about the beam of light. So is it possible for us to deflect a beam of light with the help of a strong magnet?
Yes, but we have to know whether light is a charged particle or not.
Okay.
Here, if you look at here, it looks like light, but it is not light. Now look at this. This is a tube where electron beams are created. Electron beams means charged particle. When fast moving electron is charged, when strike on some metal, it will emit X-rays. That X-ray is a electron beam. Or if you heat a filament, electron is ejected out of the filament, that is electron beam. So the ray of light, it is not light, the ray of electron beam is shown it here. When I bring magnet towards this electron beam, it is deflected. You can see that. But light is not a charged particle. Light is a neutral particle. Light is a packet of energy. So it goes as a packet of energy from one place to another place. It is neither positive nor negative. So the magnetic field cannot be deflected the light. So the answer for your question is we can't able to deflect the light with the help of magnet.
Okay, sir. Thank you for the answer. And also, it is mentioned in our NCERT textbook like two magnetic fields lines do not intersect each other. But
Yes, yes,
can we also know the reason behind this? That why is it so?
yes. Here I am showing a magnetic field of a bar magnet.
Okay.
And also when it comes together, the field is exhibited here. But look at here, there is no lines intersect. In whatever may be, whether it is uniform magnetic field or non-uniform magnetic field, in any one of the place, the magnetic field will not intersect each other, because the magnetic field direction can be represented by a tangent drawn at a point. For example, if you consider this point, I am put on red spot here, and if you want to find out the direction of the magnetic field, you have to draw a tangent like this at that point. So, wherever you want the direction of the magnetic field, you have to draw a tangent at that point. Now, I am coming to your question. There are two lines. If they are intersected, that means if I am taking two curved magnetic field A and B, if they intersect at the point P, we can draw the tangent at the point P to get the direction of the magnetic field. If I draw the tangent for A curve at P, it goes up. If I draw a tangent for the curve B at the point P, it goes down. If you look at the point P, you will get two direction for same magnetic field. So this will not be possible. At any point, the magnetic field should be in one direction only. But if it intersect, then it will show the magnetic field is in two directions. So this is not possible. So the magnetic lines never intersect. Even though they are very close to each other, they will not intersect with each other.
Okay, sir. Thank you. So, here I would like to ask the final question for this session, as we are left with a very limited time. So, sir, how is a uniform magnetic field in a given region can be represented?
Uniform magnetic field can be represented by parallel lines. Look at this bar magnet that I shown in the previous slides. Here the magnetic line starts from north pole and it ends at south pole. Now I am taking this area. Look at these two lines, whether they are parallel or non-parallel. They are non-parallel. If I take another area, they are not parallel. That means in this area the magnetic field is varying. It is not constant magnetic field. So, but look at this area. In this area the magnetic lines are represented by parallel lines. So whenever there is a magnetic field which is constant or not changing, that in that place we are representing that by a parallel lines.
Okay. So, here, sir, can you please also add something in the last of our session for all our students? Any tip or any important tip for the session regarding
Yes,
the
I
topic?
want to say one more thing. It is an important doubt that most of them have. That is,
Yes.
there are two rules in find out the magnetic field in some circuits. That is Fleming right hand rule and Fleming left hand rule. Some of the students may confuse which rule can be applied where. So both rules are giving the direction of magnetic field, current and motion or the movement of the conductor. Both left hand rule and right hand rule, both are speaking the same. If you keep our right or left hand mutually perpendicular, left of the three fingers mutually perpendicular, then each finger will represent some direction. That is the law. The Fleming right hand rule, it is created for find out the direction of current. That means if you know the motion of the conductor and magnetic field, we can find out the direction of the current. That rule is otherwise called generator rule. Because in generator, current is generated by changing the magnetic field. and the motion of the conductor. So, in that case, Fleming's left hand rule is used.
Okay, sir.
So, similarly, that motor rule or Fleming's left hand rule is used in motors. Find out the motion of the conductor. So that we have to distinguish between these. Even though both are looks same, in left hand we are find out the direction of motion of the conductor. For that we are using left hand rule. In generators we are used to find out the direction of the current. For that we are using Fleming's right hand rule.
Okay, sir. So it means we can use right hand rule and left hand thumb rule also. So thank you for this session, sir. Once again, I would like to thank you for this whole session. And as we are left with a very limited time, so we have to wrap up this session for now. And along with sir, I would also like to thank our Indian Sign Language interpreter. Thank you, Sahib Singh, for joining us. And yes, dear all learners and our viewers, let me also tell you, the new NCERT textbook for class 4th and 7th are now available on Amazon, Flipkart, and also on our NCERT official website. So please grab it on from there. And before I leave, let me tell you, within a while you can join us on channel number 6 to 12 at 4 to 5 p.m. for the session on webinar, and after that followed by 5 to 5:30 you can join us again on channel number 6 to 12 for the program of Sahyog, and at last you can join us on channel number 6, 9 and 12 for the session of NEPA. So this is all about our today's topic, and once again I would like to say thank you and namaskar.